let's talk about what kind of electric field might this make. Well, let's imagine we're really close by. We can still visualize this, what we call infinite line charge, as just being a bunch of collections of point charge. So we might say look at this part of the line and see how much that contributes field. That's positive, so it's going to go away like that. And we might pick, let's just pick a pair of points of charges on either side. So let's pick this one and pick this one. I try to draw those symmetrically. They may not be perfect, but hopefully they're supposed to be kind of representatives of paired point charges to either side, right? Because you'll have pairs, right? You'll have pairs going all the way. This is the only one that's not partnered because it's right next to the point, but then they'll be paired up going from there. So let's draw the contributions, again, radially away. So it looks like this. So that's radially away, that's like that. Radial away, that's like that. The reason they're paired up is, of course, then I can make this argument again. What happens to the vertical components? They're going to cancel out. And you can make that argument about any paired points. So we have to conclude that the electric field overall points like this, E net. So that's a point that's relatively close by. Let me take a look up at a point that's much further away. Now, one of the things you can say for sure is that each of the individual contributions, what happens is it gets larger or smaller. So if we take the same three, how are the sizes of their arrows that contributed over there? Are they bigger or smaller? Smaller, right? So for instance, the one right here is going to be smaller. That's a lot smaller. Let me draw a little bit bigger, just so that you can see it. But it's smaller than the last one. And then let me also draw the contributions. These are going to be smaller, so radially away, away. And of course, E net is in the same direction. It's still going to be to the right. And at first glance, you might think that the electric field overall is going to be smaller. So all of the electric field contributions are smaller. Contributions are all smaller. And so that would tend to make E net, so the effect on E net, that one would tend, let me just put it like this, would tend to make it smaller. All the contributors are smaller, it's going to be smaller. But this does have something going for it that the last one doesn't. And here's what it is. Notice that while these two contributed very large contributions, they're almost all vertical. So they, in very large part, cancel each other out. Here, these two contributions are smaller, but they're more forward. So they don't cancel as much. Okay? So what the contributions are all more forward. And that would actually tend to make the effect on E net, that would make it bigger. Instead of large contributions which are mostly canceling, it's smaller contributions that are more cooperative. Okay? Does that make sense? So I guess let's come up with an analogy. So let's say here, these three contributions, these are three rich households. So they all have a lot of money, but all they try to do is undercut each other, right? Try to make sure the other one gets kicked out of the country club or whatever rich people do, right? So these contributions are large, but they're mostly canceling. So here we go over to a neighborhood where Every household doesn't have that much, but they'll maybe babysit each other's kids or at least know each other's names, right? So smaller but more cooperative. Okay? So that's what's going on here. Now, you might ask, then, is it possible that this could be the same size? If I only stretch this out on the line, not quite. What we're going to have to do is take the community and not just stretch all the charges this way, but also stretch them out this way. So we'll have some neighbors, not just in this direction, but also in this other direction here. It turns out if we stretch the charge both this way and this way, then these two things exactly cancel each other out, and the net electric field is actually the same out there as it was before. Okay? So if we stretch not only in this direction, but also in this direction, I don't know how to draw this because I can't draw 3D very well. If I stretch it out in both directions into an infinite plane of charge, then these two factors cancel, and it's the same as before. So E net is actually no less all the way out here than it was right close by. All right? So it's a very bizarre charge distribution. It's an infinite plane of charge. But an infinite plane of charge can produce an electric field which is uniform, that never dies. Okay? When you are very close by, the electric field you're experiencing is due to the immediate neighbors, because most of the things that are to your flanks are mostly killing each other. But as you go far and far and far and far away, basically your field of view of things that matter to you widens out. Okay? So you start to be affected by small contributions from many, many different charges. So let me try to draw this. It looks like this. So I'm going to try to draw my 3D. I can't draw 3D, sorry. This is an infinite plane of charge. Goes out in all directions. The electric field looks like this. It's uniform. If it's a positive it'll be away, and if it's negative it'll be toward, but it never dies. Okay? It produces a uniform field on either side. So that's how you might actually form this very simple electric field, is by this weird charge configuration. You might say, isn't this silly? There's no such thing as an infinite plane of charge. Well, this is the game of physics. There aren't infinite planes of charge because it wouldn't fit in a finite universe. But there are very large planes of charge. And if you're next to a very large plane of charge, the field looks highly uniform. Okay? So let's just for kicks put together two of these planes of charge. So instead of an equal and opposite point charge, we'll put together equal and opposite infinite planes of charge. A plus and a minus. So they're smeared with the same density of plus and minus charges, and these planes go on forever. Dot, 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 so on and so forth. They get taken out in either direction. So let's go ahead and sketch out, and by the way, this thing gets a name. When you have two planes like this that are equal and opposite, we call this an infinite parallel plate capacitor. It's really useful to use as an electronics component. We'll talk about that around homework 4. So that's why it gets a special name. For right now, you don't need to know why it's called that, but I'm just kind of giving you a little bit of a preview for later. Right now, it's just two infinite planes of charge separated parallel, separated by some finite distance. Let's go ahead and sketch out what this field looks like. So positive, it goes radially away, like that, everywhere into space, and then negative, it goes radially toward, everywhere in space. So let's reason out what happens. So it should be pretty clear, what's the electric field look like between the plates? Which way does it point? It points to the right. Same reasoning as here between these two, right? In fact, since they're additive, I'm going to go ahead and draw the field line twice as dense. Because if they add, then each contributing equally, it's going to make the field strength twice as much. So the field is uniform in between the plates. Now here's the tricky part. Remember out here, right, we said that red dominates green because you're closer to the red. Out here, right, when you're closer. What happens to the red and green here? Which one dominates? They're the same, right? Because if the field never dies, then why does it matter if you're closer to one further from the other? These perfectly cancel. 0, 0. So what you have is that the electric field is uniform in between and 0 outside. Not just weak on the outsides, but actually perfectly 0. Now, if you want, we can draw in the missing link between these two. This is electric dipole. This is an infinite parallel plate cap. There is a missing link between them, and that is what we call the finite cap, the finite parallel plate cap. That's when you take your 2 point charges and you don't stretch them all the way out into an infinite plane. You just kind of make them a smaller plate like this. So we'll say that they look like this and like this. But they don't go on forever. What does the field look like for that? Well, it's basically the morphed between these two. It looks like this. In between, it's highly uniform. It starts to bow out when you get toward the edges and you start realizing these caps or these plates aren't infinite. And then when you get farther away, you can't really tell they're plates anymore anyway. They start to kind of look like point charges when you zoom out. So you can see it really is the missing link between these two extreme charge configurations. So we go from the dipole, where the field is strong in between, but then immediately starts to weaken very quickly as you go out. It's also weak out here. Then we get to the finite, where the uniformity is able to be extended a little bit between the plates, and then again starts to have this lobe shape outside. And by the time we get back to the infinite one, there's no way to approach the edge of a plate because the plates never end, and so you can maintain this uniform field everywhere between them, and the field outside is not just weak anymore, it's gone all the way to 0. So we'll come back to the cap quite a bit, but right now it's just another charge configuration that can cause a different looking field and a simple field like a uniform field. Are there any questions on that? Okay, so again, missing link. It's like that classic photo, you know, with the caveman, you know, standing up, and then he has a briefcase at the end. Okay, that's what this is. Start here, then the missing link, the Neanderthal, and then the guy with the briefcase. Okay. All right. So next order of business. Before we do the energy method, we're going to back it way up, like way up. We're going to go completely conceptual, and we're going to go back to the very earliest experience that people ever had with electricity, so that we can. So this is going to be highly conceptual discussion. We're going to catch ourselves up. So let me talk about charging by contact. This is the first that people noticed electricity, except for the possible exception of lightning. This has been known for thousands of years. You've probably charged something by contact by accident, and that's undoubtedly how people notice this phenomenon. For instance, if you scuff your feet against the carpet and then go to touch a doorknob, you notice something unusual. That's how people first started to notice electricity. So let's talk about what's going on there. When you're charging by contact, you are starting with two objects, both of which have no net charge whatsoever. They are, of course, made of normal matter, so they are made of protons and electrons, but they're basically in equal numbers, so there's no net charge overall. So then, what we do is we put them together, and I don't know how we draw this, but we rub them together. I'll explain what the rubbing does in just a second. And when we take them apart, we find that there's some kind of mysterious attraction that they're having to each other. And this is what the name that they gave to this was the electric force. So, in order to explain how in the world these two things came to attract each other, the reasoning was that for some reason they had traded something, and now they kind of wanted to get back. They want to go back on that trade. So it was Ben Franklin, actually, who supposed that there was some kind of trading going on between them, where there was some kind of particle being traded, or some kind of substance, which meant that this thing ended up with a surplus of it, and this thing ended up with a depletion of it. Okay? So hence the plus and minus. So it's thought that some positive thing was being traded, and such that it was being added to one and taken away from the other. And now what was happening was that they didn't like being apart, so they wanted to go back, hence the force. So, why plus and minus? Well, that came strictly because this was experimented upon with a large number of different substances. And these were eventually grouped into what's called a triboelectric series. Tribo just means friction, so I'll explain why the friction has to be involved. A little bit of elbow grease is necessary. You can't just touch them together. And let me give you a sample of a typical triboelectric series. Now these are just common household everyday items. Some of these are not well chemically defined. This is just an empirical thing that's done. Okay? So this is just empirical. So let me list a bunch of substances. Glass, hair, nylon, silk, fur, aluminum, paper, cotton, rubber, PVC, Teflon. I'll stop there. PVC and Teflon were not around in Ben Franklin's time. Aluminum is an element. The rest of these, there's a pretty wide variety of chemical structure that they could have. So what was found was if you rubbed these together, the things that are toward the top tended to become plus. And the more you are toward the bottom, the more you tend to become minus. Now, why plus and minus? The bookkeeping system, of course, was that any given thing, when rubbed against any other thing, it would either attract or repel other things. And there was no need to have 3 different kinds of charge. It it was found, for instance, once the convention was picked for what's plus, that everything that was attracted to it was also repelled by minus stuff. So we find that once you can pick a convention, this thing we call minus because it's attracted to plus things and it's repelled from other minuses, and so on and so forth, right? So it could well have been, and I know this is a little bit abstract, but it could well have been that there are 3 types of charge, A, B, and C. So what would have been the rules there? Well, A's repel other A's, B's repel other B's, C's repel other C's, but A's and B's, A's and C's, B's and C's all attract, right? Well, no one ever found anything that had the properties of that charge C, okay? If you actually work it out, it's impossible for something to have those properties. At some point, it would be attracting something that it should be repelling. So once it was found that everything fell into 2 categories, instead of calling them A and B, they get called plus and minus, okay? So it was assumed that there weren't 2 things being traded, there was just a single thing being traded, and so we had a plus indicating that something was being gained, and minus indicating something was lost, okay? So for instance, things, if you combine glass and Teflon, and you rub them together, you can most assuredly depend that glass is going to be plus and Teflon is going to be minus. In fact, there will be a lot of transferring because there are such extremes in terms of what they want. The glass likes to become plus, and the Teflon likes to become minus, and so there's no question what's going to happen. Now, before I go too much further, I should let you know that Ben Franklin had a 50-50 chance of getting this right, and he got it wrong. He arbitrarily picked some substance, I forget what it was like glass or silk or something, as having the plus charge, and he was wrong. And in fact, if you had a very precise scale in this situation, you would actually find that this one is the one that lost mass, and this one gains mass. So there goes right out the window. Whatever arbitrary decision you made about who's gaining and who's losing was dead wrong. He wanted to call it plus because he thought it was gaining something, it was actually losing mass, and the thing that he wanted to call minus because it was depleted is actually the one that gains it. And so this is how the electron got its minus sign. What's really being exchanged here is electrons. Particles are going the other way. And since the convention had already been chosen by Franklin, that's how the electron was simply assigned a minus sign. So there's really, what's going on is electrons are exchanged the other way. And so when something becomes minus, it's not because it's losing anything, it's gaining minus charge. And when something becomes positive, it's not really gaining anything, it's actually losing electrons, which are negative, therefore it's becoming positive because it's being depleted. So now you know how the electron got its minus sign. We will find that the electrons being on the outside of atoms are almost always being exchanged. They're the movers and shakers here for charge exchange. But because the conventions had already long been chosen before that, the electron, when it was discovered, was given the minus sign. Okay. By the way, I should point out that all we're doing here is exchanging electrons from here to here. So these things overall, we're neutral to start with. They have to be neutral to end with. It's just that the charge has been sloshed over. So the sum of the 2 charges remains 0. You can't just create electrons out of thin air or destroy them into thin air. You can just take them from one to the other. So in this case, Q1 becomes plus, Q2 becomes minus, but everything is still there. You still have an equal number of protons and electrons in your system. Okay, so you've just made an imbalance of those electrons. So, the positive, things that tend to become positive, these are things that like to give away electrons. We like to call them electron donators. And the things that tend to become minus charged are called electron acceptors. They like to gain electrons. At this point, you might be thinking electronegativity, which is a more formalized way of thinking about this. But I should emphasize that the triboelectric series is really highly empirical. So think of it as just kind of more rough way to rank how much something wants to gain electrons versus lose electrons. You guys already know about valence shells, right? Depending on your chemical structure, maybe you would prefer to fill in your valence shell by getting a few extra electrons. Those are your acceptors. If you could ditch a few and have a full valence shell, then you're more likely to be a donator, right? So if you combine a very good donator with a very good acceptor, they're pretty happy to meet each other, right? One wants to give up electrons, one wants to gain it. So we'll have a lot of charge transfer.